So today I won't be streaming for long. I think I'll stay here for only 1 hour because I have a bunch of stuff to do off stream. So just gonna read the book again. Yeah, start the timer. Introduction to fundamental data types. Bits, bytes, and memory addressing. In lesson 1.3, Introduction to Objects and Variables, we talked about the fact that variables are names for a piece of memory that can be used to store information. To recap briefly, computers have random access memory. It is available for programs to use. When the variable is defined, a piece of memory is set aside for that variable. The smallest unit of memory is a binary digit, also called a bit, which can hold a value of 0 or 1. You can think of bits as being like tradition. So this is just the basic explanation of memory, I guess. C++ we typically work with byte-sized chunk data. The following picture shows some sequential memory addresses along with the corresponding bytes of data. As an aside, some older or non-standard machines may have bytes of a different size from 1 to 48 bits. However, we generally need not worry about this, as the modern de facto standard is that a byte is 8 bits. Registers will assume a byte is 8 bits. Data types. Because all data on a computer is just a sequence of bits, we use a data type, often called a type for short, to tell the compiler how to interpret the contents of memory in some meaningful way. I've already seen one example of data type, the integer. When we declare a variable as an integer, we are telling the compiler the piece of memory that the variable used is going to be interpreted as an integer value. When you give an object a value, the compiler and CPU take care of encoding your value into the appropriate sequence of bits for that data type, which are then stored in memory. Remember, memory can only store bits. For example, if you assign an integer object the value 65, the value is converted to the sequence of bits 101 and stored in the memory assigned to the object. Conversely, when the object is evaluated to produce a value, the sequence of bits is reconstituted back into the original value, meaning that 101 is converted back into the value 65. Fortunately, the compiler and CPU do all the hard work here, so you generally don't need to worry about how values get converted into bit sequences and back. All you need to do is pick a data type for a project that best matches your desired use. Fundamental data types. C++ comes with built-in support for many different data types. These are called fundamental data types, but are often informally called basic types, primitive types, or built-in types. Here's a list of the fundamental data types, some of which you have already seen. So float double, long double, bool, char, short, int, long. This chapter is dedicated to exploring these fundamental data types in detail. Standard no pointer t to discuss and talk about pointers, except this when we discuss pointers. C++ also supports a number of other more complex types called compound types. We will explore compound types in a future chapter. Author's note: the terms integer and integral are similar, but have different meanings. Integer is a specific data type that have no fractional numbers. I don't think I need to read this. As an aside, most modern programming languages include a fundamental string type. Strings are data that lets us hold a sequence of characters typically used to represent text. C++ strings aren't a fundamental type, they're a compound type. But because basic strings usage is straightforward and useful, introduce strings in this chapter as well. The th suffix. Many of the types defined in newer versions of C++ use a th suffix. This suffix means type, and its common nomenclature applied to modern types. If you see something with a th suffix, it's probably a type, but many types don't have a th suffix, so this isn't consistently applied. Void is the easiest of data types to explain. Basically, void means no type. Consequently, variables cannot be defined with a type of void. Void is typically used in several different contexts. Functions that do not return a value. Most commonly, void is used to indicate a function that doesn't return a value. If you use return statements to try to return the values in such function, a compiler will occur. Deprecated functions that do not take parameters. In C, void is used as a way to indicate that a function does not take any parameters. Void here means no parameters. Although this will compile in C++ for backwards compatibility reasons, this use of keyword voids is considered deprecated in C++. The following code is equivalent and preferred in C++. Best practice. Yeah, it's kind of redundant. Sure. Just type void there every time. Use an empty parameter list instead of void to indicate that a function has no parameters. Other uses of void. Void keyword as a third more advanced use in C++ will cover in section void pointers. Since you haven't covered what pointer is yet, you don't need to worry about. Object sizes and the size of operator. As you learned in the lesson, memory on modern machines is typically organized into byte-size units, with each byte of memory having a unique address. Up to this point, it has been useful to think of memory as a bunch of cubby holes or mailboxes where we can put and retrieve information, and variables as names for accessing those cubby holes or mailboxes. However, this analogy is not quite correct in one regard. Most objects actually take up more than 1 byte of memory. A single object may use 2, 4, 8, or even more consecutive memory addresses. The amount of memory that an object uses is based on its type. Because it typically accesses memory through variable names and not directly via memory addresses, the compiler is able to hide the details of how many bytes a given object uses from us. When you access some variable x, the compiler knows how many bytes of data to retrieve based on the type of variable x and can handle that task for us. Even so, there are several reasons it is useful to know how much memory an object uses. First, the more memory an object uses, the more information it can hold. A single bit can hold 2 possible values, 0 or 1. 2 bits can hold 4 possible values. 3 bits can hold 8 possible values. To generalize an object with n bits, where n is an integer, can hold n, 2 elevated to n, also commonly written like this, unique values. Therefore, with an 8-bit byte, a sized object can hold 2 to the power of 8, 256 different values. An object that uses 2 bytes can hold 2 to the 16 different values. Thus, the size of the object puts a limit on the amount of unique values it can store. Objects that utilize more bytes can store a larger number of unique values. We will explore this further when we talk about integers. Second, computers have a finite amount of free memory. Every time we define an object, a small portion of that free memory is used for as long as the object is in existence. Because modern computers have a lot of memory, this impact is usually negligible. However, for programs that need a large amount of objects or data, game that is rendering millions of polygons, the difference between using 1 byte and 8 bytes objects can be significant. Key insight. New programmers often focus too much on optimizing their code to use as little memory as possible. In most cases, this makes a negligible difference. Focus on writing maintainable code and optimizing only when and where the benefit will be substantive. Fundamental data type sizes. The obvious next question is how much memory do variables of different data types take? We may be surprised to find that the size of a given data type is dependent on the compiler and/or the computer architecture. C++ only guarantees that each fundamental data type will have a minimum size. So bool is 1, character 1, integer 2, long 4, long 8, float 4, double 8, long double 8. How is exactly 1 byte? So it takes 256, way more instructions to create a floating point. Yeah, not sure if I remember correctly from the other page. Here, actually. An object with n bits can hold 2 to the n. So 8 bytes is a lot more. Yeah, byte-sized object can hold 256 values. So this can hold around 1600, 1700. This holds 1600, 1700 set of instructions in binary, which is crazy. Means that it takes 256 lines of machine code to create a floating point. Is this correct? It seems like it's a lot for. It probably is correct, but however, the actual size of the variables may be different on your machine. For maximum compatibility, you shouldn't assume the variables are larger than the specified minimum size. Objects of fundamental data types are generally extremely fast. The size of operator. In order to determine the size of data type on a particular machine, C++ provides an operator named sizeof. Sizeof operator is a unary operator that takes either a type of or a variable and returns its size in bytes. You can compile and run the following program to find out how large some of your data types are. Here's the output that the author got. Visual Studio. Your results may vary if you are using a different type of machine or a different compiler. Note that you cannot use the sizeof operator on the void type, since it has no size. Doing so will cause a compiler error. For advanced readers, if you're wondering what T is in the above program, it's a special symbol that inserts a tab. In example, we're using each to align the output columns. We will cover T and other special symbols in lesson 4.11. So T here. T is to align. You can also use the sizeof operator on variable name. Fundamental data types, data type performance. On modern machines, objects of the fundamental data types are fast. The performance while using these types should generally not be a concern. As an aside, you might assume that types that use less memory would be faster than types that use more memory. This is not always true. CPUs are often optimized to process data of a certain size, and types that match that size may be processed quicker. Such a machine, a 32-bit int could be faster than a 16-bit short or an 8-bit character. So I think these values might be useful to 2 to the power of n amounts that a bit can hold. 2 to the power of 8 equals bytes, which is holds 256. Different values. Binary. So it's useful to have in the back of my head because then I can know. And I probably should take a picture of this table here, just so I have it. This will save later, I think. So it's useful to know when I'm going to create programs so I can separate the size of the program, size of each thing according to the trying to hit 64-bit or 32. My computer is 64 architecture, so probably 64 when I'm building stuff from my own operating system and try to hit. But yeah, it's probably best practice to always try to, after you do all the code and it works and you optimized other things, then I think the final thing is probably this bit size stuff. Signed integers. An integer is an integral type that can represent positive and negative whole numbers, including 0 and this stuff. C++ has 4 different fundamental integer types available for use. Short, int, long, long. No, wasn't it different number there? It's only 4 bytes. Typically 32 bits on modern architecture. The key difference between the various integer types is that they have varying sizes. The larger integers can hold bigger numbers. Makes sense. So when you're using a very big number, or I think we're gonna use a very big number, you should use the other ones instead of int in short for short numbers. A reminder, C++ only guarantees that integers will have a certain minimum size, not that they will have a specific size. Signed integers. When writing negative numbers in everyday life, we use a negative sign. For example, -3 means -3. We also typically recognize +3 as positive, though a common convention dictates that we typically omit plus prefixes. This attribute of being positive, negative, or 0 is called the number sign. By default, the integer is assigned, which means the number sign is stored as a part of the number. This is a single bit called the sign bit. Therefore, a signed integer can hold both positive and negative numbers and 0. In this lesson, we will focus on signed integers. We'll discuss unsigned integers, which can only hold non-negative numbers in the next lesson. Related content. We'll discuss how the sign bit is used when representing numbers in binary lesson, and this lesson here. Defining signed integers. Here's the preferred way to define the 4 types of signed integers. All of the integers except int can take an optional int suffix. This suffix should not be used. In addition to being more typing, adding the int suffix makes the type harder to distinguish from variables of type int. This can lead to mistakes if the short or long modifier is inadvertently missed. The integer types can also take an optional sign keyword, which by convention is typically placed before the type name. However, this keyword should not be used as it is redundant since integers are assigned by default. Best practice, prefer the shorthand types that do not use this int suffix or sign prefix. Signed integer ranges. As we learned in the last section, a variable with n bits can hold true and possible values. But which specific values? Call the set of specific values that a data type can hold its range. The range of an integer variable is determined by 2 factors: its size in bits and whether it is signed or not. By definition, an 8-bit signed integer has a range of -128 to 127. This means a signed integer can store any integer value between -128 and 127 inclusive safely. So I think I'm gonna copy this here. As an aside, math time, an 8-bit integer contains 8 bits. 256, an 8-bit integer count 356 possible values. There are 356 possible values between this includes. Yeah. Here's a table containing the range of signed integers of different sizes. For the math inclined, an n-bit signed variable has a range of yeah, I think it's minus 2 elevated by n minus 1 and 2 elevated by n minus 1 minus 1 to the power of, I should say elevated because Portuguese makes more sense. For the no math inclined, use the table. N-bit signed variable has a range of. So I think this is a good thing to also take a picture of. Integer overflow. What happens if we try to assign the value 280 to an 8-bit signed integer? This number is outside the range that a 8-bit signed integer can hold. 280 to an 8-byte integer. Number 280 requires 9 bits plus 1 signed bit should be represented. But we only have 7 bits plus 1 signed bit available in an 8-bit signed integer. So yeah, 9 bits plus 1 signed bit. Because it passes 256, which is the thing, I think. I'm trying to think about how the int relates to the number itself, because int is 4 bytes. And then the value, I think, yeah, I think the value is 1 byte each to be stored. I'm not really sure. I think it depends on the translation of the value to binary. It's probably a one-to-one translation, where you don't need to have an extra program to convert from the numbers we use to the binary thing. But I'm not sure. Integer overflow. Often called overflow for short, occurs when we try to store a value that is outside of the range of the type. Essentially, the number we are trying to store requires more bits to represent than the object has available. In such a case, data is lost because the object doesn't have enough memory to store everything. In the case of signed integers, which bits are lost is not well defined. The signed integer overflow leads to undefined behavior. Warning, signed integer overflow will result in undefined behavior. In general, overflow results in information being lost, which is almost never desirable. If there's any suspicion that an object might need to store a value that falls outside its range, use a type of a bigger range. But what if you have a bigger number than this? Yeah, but that's very big. When dividing two integers, C++ works like you'd expect when the quotient is a whole number. This produces the expected result 5. But let's look at what happens when integer division causes a fractional result. This produces a possibly unexpected result. 1. When doing division with two integers called integer division, C++ always produces an integer result. These integers can't hold fractional values. Any fractional portion is simply dropped, not rounded. Taking a closer look at the above example, 8 divided by 5 produces the value 1.6, the fractional set of 6 is dropped, and 1 remains. Be careful when using integer division, as you lose any fractional parts of the quotient. However, if it is what you want, integer division is safe to use, as the results are predictable. If fractional results are desired, we showed the method to do this in this class. So I'm still not 100% sure if I understand correctly how the variables are become the bit size, because that's a little bit confusing. The int type has four bytes, and then the number requires different bytes. The operator probably requires different bytes as well, different bits. So what I got so far is that you should prefer to use data types that contain the amount of space, the amount of memory that you want to use for specific things. But as how exactly these things are stored in memory, I still don't understand really well, I think. Because for me, the int is probably stored somewhere, and then the number that it holds is stored another place. It's kind of confusing to think, but I guess the translation is 1 to 1. So a 280 number is gonna have the equivalent amount in bits that requires should should make the transformation, the mathematical transformation between the base 10 and the bits number system. But I'm not sure if there are additional instructions that are needed to convert them, because otherwise, how would the computer do it? But maybe that's the way that it is stored in memory, that it's just, yeah, I'm not sure. Unsigned integers and why to avoid them. Unsigned integers, in the previous lesson, we covered signed integers, which are a set of types that can hold positive and negative whole numbers, including 0. C++ also supports using unsigned integers. Unsigned integers are integers that can only hold non-negative whole numbers. To define an unsigned integer, we use the unsigned keyword. By convention, this is placed before the type. Unsigned integer range. A 1-bit unsigned integer has a range of 0 to 255. Compare this to 1 byte signed integer. Both can start 256, but signed integers use half the range. An n-bit, the unsigned variable, has a range of 0 to this number. When no negative numbers are required, unsigned integers are well suited for networking in systems with little memory, because unsigned integers can store more positive numbers without taking up extra memory. Remember the terms signed and unsigned. New programmers sometimes get signed and unsigned mixed up. The following is a simple way to remember the difference. Unsigned integer overflow. What happens if you try to store the number 280, which requires 9 bits to represent, in a 1 byte 8-bit unsigned integer? The answer is overflow. Oddly, the C++ standard explicitly says a computation involving unsigned operands can never overflow. This is contrary to general programming consensus that integer overflow encompasses both signed and unsigned use cases. Given that most programmers would consider this overflow, we'll call this overflow despite C++ statements to the contrary. If an unsigned value is out of range, it is divided by 1 greater than the largest number of the type, and only the remainder kept. The number 280 should be fit in our 1 byte range of 0 to 255. 1 greater than the largest number of the type is 256. Therefore, we divide 280 by 256. That's how it is, like I was imagining. getting one remainder 224. The remainder of 24 is what is stored. One remainder 24. Here's another way to think about the same thing. The number bigger than the largest number representable by the type simply wraps around, sometimes called module wrapping. 255 is a range of a 1 byte integer. So 255 is fine. 256, however, is outside the range. So it wraps around to the value 0. 257 wraps around to the value 1.280. 1 to 80 wraps around the value to the value 24. So 256 wraps to 0, 257 wraps to 1, and 280 wraps to. So whatever the remainder is going to be what's saved. Let's take a look at this using 2-byte integer. What do you think the result of this program will be? Man, this is really crazy if you have to keep in mind all these numbers while you're programming. And it's weird that the course didn't mention that. Not sure if this is required or is just best practice. It seems like it is required from the way they are writing. But then I don't understand why the course wouldn't mention this, the Code Academy course. What do you think the result of this program will be? So 0 and 1 because it passes the range. It's possible to wrap around the other directions as well. 0 is representable in a 2-byte unsigned integer, so that's fine. -1 is not representable. So it wraps around to the top of the range, producing this value. -2 wraps around to this, and so forth. The above code triggers a warning in some compilers. Because the compiler detects that the integer literal is out of range for the given type. If you want to compile the code anyway, temporarily disable treat warnings as errors. There's an assigned many notable bugs in video game history happen due to wraparound behavior with unsigned integers. The arcade game Donkey Kong, it's not possible to go past level 22 due to an overflow bug that leaves the user with not enough bonus time to complete the level. In the PC game Civilization, Gandhi was known for often being the first one to use nuclear weapons, which seems contrary to his expected passive nature. Players believed this was a result of Gandhi's aggression setting was initially set at 1. But if he chose a democratic government, he got a -2 modifier. This would cause his aggression to overflow to 255, making him maximally aggressive. However, more recently, Sid Meier, the game's author, clarified that this wasn't actually the case. The controversy over unsigned numbers. Many developers and some large development houses, such as Google, believe that developers should generally avoid using unsigned integers. This is largely because of two behaviors that can cause problems. First, consider the subtraction of two unsigned numbers, such as 3 and 5, is -2, but -2 can't be represented as an unsigned number. On the author's machine, this seemingly innocent looking program produces the result because, okay, this occurred due to the -2 wrapping property. Another common unwanted wraparound happens when an unsigned integer is repeatedly decremented by 1. Second, an unexpected behavior can result when you mix signed and unsigned integers. In a mathematical operation C++, arithmetic or comparison, if one signed and one unsigned integer are used, signed integer will be converted to unsigned. And because unsigned integers cannot store negative numbers, this can result in loss of data. Consider the following program demonstrating this. This program is well formed, compass, pretty redundant. Additionally, there are other problematic cases that are essentially undetectable. Consider the following. So subtracting -1. Yes, so it's obviously a problem there. Now to reduce something as expect someone to call this function only positive. Best practice. Favor signed numbers over unsigned numbers for holding quantities, even quantities that should be non-negative in mathematical operations. Avoid mixing signed and unsigned numbers. So when should you use unsigned numbers? There are still a few cases in C++ when it's okay and necessary to use unsigned numbers. First, unsigned numbers are preferred when dealing with bit manipulation, covered in chapter O, that's capital O, not a zero. They are also useful when well-defined wraparound behavior is required, used when some algorithms like encryption and random number generation. Second, the use of unsigned numbers is still unavoidable in some cases, mainly those having to do with array indexing. We'll talk more about this in the lesson arrays and array indexing. This, in these cases, the unsigned value can be converted to a signed value. Also note that if you're developing for an embedded system, Arduino or some other processor memory limited context, use of unsigned number is more common and accepted, and in some cases unavoidable for performance reasons. Fixed with integers and syzes. In the previous lesson on integers, we covered that C++ only guarantees that integer variables will have a minimum size, but they could be larger depending on the target system. Why isn't the size of the integer variables fixed? Short answer is that this goes back to C when computers were slow and performance was of the utmost concern. C opted to intentionally leave the size of an integer open so that the compiler implementers could pick a size for int that performs best on the target computer architecture. Doesn't this suck by, by modern standard? Yes. The program is a little ridiculous to have to deal with types and that have uncertain ranges. Consider the int type. The minimum size for int is 2 bytes, but it is often 4 bytes on modern architectures. If assume an int is 4 bytes because that's most likely, then your program will probably misbehave on architectures where int is actually 2 bytes. Since you'll probably be storing values that require 4 bytes in a 2-byte variable, which will cause overflow or undefined behavior. If assume an int is only 2 bytes, to ensure maximum compatibility, then on systems where int is 4 bytes, you're wasting 2 bytes per integer, and doubling your memory usage. Fixed with integers. To address the above issues, C99 defines a set of fixed with integers in the standard int.h header that are guaranteed to be the same size on any architecture. These are defined as follows. On bytes, sign and signed. Treated like a signed chart on many systems seen below. And signed. C++ officially adopted this fixed width integers as part of C++ 11. It can be accessed by including the C standard int header, where they are defined inside it and inside the standard namespace. Here's an example. So maybe that's good to. I think I'm gonna create a folder just for this type of stuff, so I have it easily accessible in a way that I know where it is. the fixed width integers have the two downsides that are typically raised. First, the fixed width integers are not guaranteed to be defined on all architectures. They only exist on systems where there are fundamental types matching the widths and following a certain binary representation. A program fails to compile on any search architecture that does not support fixed width integer texture program is using. However, given that most modern architectures have it standardized around 8, 16, 32, 64-bit variables, it's unlikely to be a problem unless your program needs to be portable to some exotic mainframe or embedded architectures. Second, if you use a fixed width integer, it may be slower than a wider type on some architectures. For example, if you need an integer that is guaranteed to be 32 bits, you might decide to use standard 32, but your CPU might actually be faster at processing 64-bit integers. However, just because your CPU can process a given type faster doesn't mean your program will be faster overall. Modern programs are often constrained by memory usage rather than CPU. And the larger memory footprint may slow your program, or the faster CPU processing accelerates it. It's hard to know without actually measuring. Fast and least integers. To help address the above downside, C++ also defines two alternative sets of integers that are guaranteed to be defined. The fast types, standard fast and standard youth fast, provide the fastest signed and unsigned integer types. Integer type with a width of at least hashtag bits. Will give you fastest signed integer type that's at least 32 bits. Last types, standard in last and standard in last, provide the smallest signed unsigned integer type with a width at least. For example, we'll give you 32 bits. This is an example from the author's Visual Studio 32-bit console application. So at least 8, least 16. This produces the result. You can see that standard int list 16 is 16 bits, whereas standard int fast 16t is actually 32 bits. This is because on the author's machine, 32 bits integers are faster to process than 16-bit integers. However, these fast and least integers have their own downsides. First, not many programmers actually use them, and a lack of familiarity can lead to errors. Second, the fast types can lead to the same kind of memory wastage that we saw with 4-byte integers. Most seriously, because the size of the fast list integers can vary, it's possible that your program may exhibit different behaviors on architectures where they resolve to different sizes. Just writing this down, so I'll write on the title later. Scoder produces different results depending on whether it's hard to know where your program might not function as expected until you've rigorously tested your program on such architectures. I imagine not many developers have access to a wide range of different architectures to test with. So far, this has been the most interesting portion of the book, I think, for me. Because this is starting to get into how to actually visualize what's happening in memory while you code. And I wonder, another question I have is if I'm gonna perform calculations that are not, if I'm gonna do a bunch of things with the numbers, then how I'm gonna know what sizes to use if I don't know if what the resulting number will be necessarily. So this is also an interesting thing I think to think about. And I wonder how people, another thing is how people actually use this in practice, because I haven't seen many, but to be fair, I haven't seen a lot of code in C++, but at least in the other languages, people don't care at all about this stuff, and I didn't care at all as well. And it seems like it will be very hard to keep this in mind while I do things. It seems like more of a cherry on the top, but I'm not sure if it's a necessity or the normal way people do things when writing code on C++. Standard int and uint likely behave like chars instead of integers, which an oversight in the C++ specification. Most compilers defining treats standard int at and uint at and their corresponding fast and least fixed with types, and they identically to types signed char and unsigned char, respectively. This means these 8-bit types may or may not behave differently than the rest of the fixed with types, which can lead to errors. This behavior is system dependent, so a program that behaves correctly on one architecture may not compile or behave correctly on another architecture. I also forgot which one stands for. Yeah, so the normal one stands for the normal, with the U is unsigned. That makes sense because for obvious reasons. For consistency, it's best to avoid and the related best and least types altogether. Use standard int 16, uint 16 stuff. Avoid the 8-bit fixed with integer types. If you do use them, note that they are often treated like chars. Integral best practices. Given the various pros and cons of the fundamental integral types, the fixed with integral types, the fast these integral types, and signed and unsigned challenges, there is a little consensus on integral part best practice. Our stance is that it's better to be correct than fast, better to fail as compile time than runtime. Therefore, we recommend avoiding the fast least types in favor of the fixed with type. If you later discover the need to support a platform for which the fixed with types won't compile, then you can decide how to migrate your program and thoroughly test at that point. Best practice. Prefer int when the size of integer doesn't matter, e.g. the number will always fit within the range of a 2-byte signed integer. For example, if we're asking the user to enter their age or counting from 1 to 10, it doesn't matter whether int is 16 or 32 bits. The numbers will fit either way, unless they put some malicious stuff just to break the code. If they put a very large number. I wouldn't do this when asking for inputs, so I would only do it if it's an internal function, private function, that I know is going to be consistent every time. This will cover the vast majority of cases you're likely to run across. First, enter entity when storing a quantity that needs a guaranteed range. Prefer uentity when doing a bit manipulation or where well-defined wraparound behavior is required. Avoid the following when possible. Unsigned types for holding quantities, the 8-bit fixed with integer types, the fast and least with fixed with types, any compiler specific fixed with integers. For example, Visual Studio defines int 18 and 16. What is standard syzes? Consider the following code. On the author's machine, this prints 4. Pretty simple, right? We can infer that the operator size of returns an integer value. But what integer type is that return value? An int, a short? The answer is that size of, and many functions that return a size or length value return a value of type standard syzes. Standard syzes is defined as an unsigned integral type and is typically used to represent the size of length of objects. Assumingly, we can use the size of operator which returns a value of type standard syzes just for the size standard syzes itself. Compile as a 32-bit 4-byte console app on the author system, this prints 4. Much like an integer can vary in size depending on the system, standard syzes also varies in size. Standard size also varies in size. Standard syzes is guaranteed to be unsigned in at least 16 bits. but most systems will be equivalent to the address width of the application. That is, for 32-bit applications, standard size T will typically be a 32-bit unsigned integer. For 64, it will be 64. This is defined to be big enough to hold the size of the largest object creatable in your system in bytes. For example, if size T is 4 bytes wide, the largest object creatable in your system can't be larger than 4 billion something, because this is the largest number of 4 bytes unsigned integer can store. This is only the uppermost limit of an object's size. The real size limit can be lower depending on the compiler you're using. By defining any object with a size in bytes larger than the largest integral value size T can hold, is considered U-form and will cause a compiler error. The size of operator will not be able to return the size without wrapping around. See how much time I have. 9 minutes. Introduction to scientific notation. Before I talk about our next subject, we're going to sidebar into the topic of scientific notation. Scientific notation is as useful shorthand for writing lengthy numbers in a concise manner. Although scientific notation may seem foreign at first, understanding scientific notation will help you understand how floating points numbers work. More importantly, what their limitations are. Numbers in scientific notation take the following form: significand times 10 to the power of exponent. For example, in the scientific notation, is significant and 4 is the exponent. 1.2 is significant 4. Since 10 to the power of 4 elevates to 10,000, the convention numbers in scientific notation are written with the one digit before the decimal point and the rest of the digits afterwards. Consider the mass of the Earth in decimal notation. We write this as this. It's a really large number, too big to fit even in an 8-byte integer. It's also hard to read. Is that 19 or 20 zeros? Even separators, the number is still hard to read. In scientific notation, this would be written as 24, which is much easier to read. Scientific notation has the added benefit of making it easier to compare the magnitude of two really large or really small numbers simply by comparing the exponent. Because it can be hard to type or display exponents in C++, we use the letters E or sometimes E to represent the times 10 to the power of part of the equation. For example, this would be written as this, and this would be written. So it's just type the number, then E, and then the exponent. For numbers smaller than 1, the exponent can be negative. The numbers is equivalent to this. The mass of an electron is this one. How to convert numbers to scientific notation? Use the following procedure. The exponent starts at 0, beside the decimal, so there is only one non-zero digit to the left of the decimal. Each place you slide the decimal to the right increases the exponent by 1. Each place you slide the decimal to the left increases by 1, to the right decreases by 1. Trim off any leading zeros on the left is the signal. Trim off. So basic stuff, mathematics. Here's the most important thing to understand. The digits in the significant, the part before the E, are called the significant digits. The number of significant digits defines the number's precision. The more digits in the significant, the more precision the number is. Precision training zeros after the decimal. Consider the case where we ask two lab assistants each to an apple. I think this part is really redundant. We just talk about mathematics, not the code part, which I already know. I think I'll read this last one page, 5 minutes, then I'll be done. Floating point numbers. Integers are great for counting whole numbers, but sometimes we need to store very large numbers, or numbers with a fractional component. A floating point type variable is a variable that can hold a real number, such as this is the floating point. The floating part of the name floating point refers to the fact that the decimal point can float. That is, it can support a variable number of digits before and after this decimal point. A question just popped in my mind, which is I wonder if there's a best way to represent imaginary numbers, or just use a random library to take the square root and start as square root of -1. There are three different floating point data types: float, double, and long double. As with integers, C++ does not define the actual size of these types, but it does guarantee the minimum size. On modern architectures, floating point representation almost always follows this binary format. This format, a float is 4 bytes, double is 8, and a long double can be equivalent to a double, 8 bytes. So a float is 4, double is 8. 8 bits, 8 bits often padded to 12 bytes or 16 bytes. Okay. Floating point data types are always signed, count positive and negative. Floating for picture. Here are some definitions of floating point numbers. And using floating point literals always include at least one decimal place, even if the decimal is 0. This helps the compiler understand that the number is a floating point number and not an integer. Note that by default, floating point literals default to type double. An F suffix is used to denote a literal of type float. Always make sure the type of your literals match the type of the variables they're being assigned to or used to initialize. Otherwise, unnecessary convention will result, possibly flaws of precision. Make sure you don't use integer literals where floating point literals should be used. This includes when initializing or assigning values to the floating point objects. Doing floating point arithmetic and calling functions and expect floating point values. So make sure you don't use integer literals where floating points literals should be used. Don't use integer literals where yeah. Initializing, so okay. Printing floating point numbers. Now consider the simple program. The result is simple, may surprise you. The first case, standard count printed 5, even though we typed in 5.0. By default, standard count will not print the fractional part of a number if the fractional part is 0. The second case, the number prints as we expected. The third case, it printed the number in the certificate notation. Need a refresher. Yeah, so it saves memory probably. Floating point range. Summary 75 for representation. So precision 6 to 9 significant digits, typically 7. 15 to 18. 18. The 80-bit floating point type is a bit of a historical anomaly. On other processors, it is typically implemented using 12 or 16-bit bytes, which is more natural size for processors to handle. It may seem a little odd that the 8-bit floating point type has the same range as the 16-byte floating point type. This is because they have the same number of bits dedicated to the exponent. However, the 16-byte number can store more significant digits. Not sure if I fully got this. Floating point range. Then I'm gonna save it. Floating point precision. Consider the fraction 1/3 the decimal representation of this number is 0.33 if 3 is going out to infinity. If you were writing this number on a piece of paper, your arm would get tired at some point, and you'd eventually stop writing. And the number you were left with would be close to this, with 3 is going out to infinity, but not exactly. On a computer, an infinite length number would require infinite memory to store, and typically we only have 4 or 8 bytes. This limited memory means floating point numbers can only store a certain number of significant digits, and that any additional significant digits are lost. The number that is actually stored will be close to the desired number, but not exact. The precision of a floating point number defines how many significant digits it can represent without information loss. And outputting floating point numbers, standard count has a default precision of 6. That is, it assumes that all floating points variables are only significant to 6 digits, the minimum precision of a float, and hence it will truncate anything after that. The following program shows standard count truncated to 6 digits. The program returns this. Note that each of these only has 6 significant digits. Also note that standard count will switch to outputting numbers in scientific notation in some cases. Depending on the compiler, the exponent will typically be padded to a minimum number of digits. Here or not, this number is the same as this, just with some padding zeros. The minimum number of exponent digits displayed is compiler specific. Visual Studio uses 3, some others is issue, as per the C99 standard. The number of digits of precision floating points variable of the number of digits of a precision floating point variable depends on both the sizes. Floats have less precision than doubles. In particular values the particular value being stored, some values have more precision than others. Float values have between 6 and 9 digits of precision, with most float values having at least 7 significant digits. Double values have between 15 and 18 digits of precision, with most double values having at least 16 significant digits. Long double has a minimum precision of 15, 18, or 33 significant digits, depending on how many bytes it occupies. You can override the default precision that standard count shows by using an output manipulator function named standard set precision. Output manipulators alter how data is output and are defined in the IO manip header. So this library here, header, I should say. Because we set the precision to 16 digits, standard set precision, each of the above precision is printed with 16 digits, but as you can see, the numbers certainly are precise to 16 digits. And because floats are less precise than doubles, the float has more errors. Precision issues don't just impact fractional numbers, they impact any number with too many significant digits. Let's consider a big number. And is greater than this, the value has 10 significant digits, but float values typically have 7 digits of precision. The result is precise only to 7 significant digits. Loss in precision. When precision is lost because a number can't be stored precisely, this is called a rounding error. Consequently, one has to be careful when using floating point numbers that require more precision than the variables can hold. Best practice: favor double overflow unless space is at a premium, as a lack of precision in a float will often lead to inaccuracies. Rounding errors make floating point comparisons tricky. Floating point numbers are tricky to work with due to non-obvious differences between binary, how data is stored, and decimal, how we think numbers. Consider the fraction 1 divided by 10. In decimal, this is easily represented as 0.1, and we are used to thinking of 0.1 as an easily representable number with one significant digit. However, in binary, 0.1 is represented by the infinite sequence this. Because of this, when we assign 0.1 to a floating point number, we run into precision problems. You can see the effects of this in the following program. That's very interesting. This outputs this. On the top line, standard count prints 0.1 as we expect. On the bottom line, when we have standard count show 17 digits of precision, we see that this is actually not quite 0.1. This is because the double had to truncate the approximation due to its limited memory. The result is a number that is precise just 16 significant digits, which type double guarantees, but the number is not exactly 0.1. Rounding errors may make a number either slightly smaller or slightly larger, depending on where the truncation happens. Rounding errors can have unexpected consequences. Although we might expect that D1 and D2 should be equal, we see that they are not. If you compare D1 and D2 in your program, the program would probably not perform as expected because floating point numbers tend to be inexact. Comparing floating point numbers is generally problematic. We discussed the subject more and solutions in lesson. One last note on rounding errors: mathematical operations, such as addition and multiplication, tend to make rounding errors grow. So even though 0.1 has a rounding error in the 17th significant digit, when we add 0.1 10 times, the rounding error has scrapped to the 16th significant digit. Continued operations would cause this error to become increasingly significant. Key insight: rounding errors occur when a number can't be stored precisely. This can happen even with simple numbers like 0.1. Therefore, rounding errors can and do happen all the time. Rounding errors aren't the exception, they are the rule. Never assume your floating point numbers are exact. A corollary of this rule is be wary of using floating point numbers for financial or currency data. That's very, very interesting. None and inf. There are two special categories of floating point numbers. The first is inf. I'm not sure what this is. Oh, so it's cautious in this word here. Such a weird word. Never seen that before. Whatever. Inf stands for infinity and int stands for indeterminate. Note that the results are printing inf and none are platform specific, so our results may vary. Oh, I jumped all of this stuff. There are two special categories of floating point numbers. The first is inf, which represents infinity. Inf can be positive or negative. The second is none, which stands for not a number. There are several different kinds of none, which we won't discuss here. None and inf are only available if the compiler uses a specific format for floating point numbers. If another format is used, the following code produces an undefined behavior. Inf stands for infinity and stands for indeterminate. Avoid division by zero altogether, even if your compiler supports it. Conclusion: to summarize the two things you should remember about floating point numbers. Floating point numbers are useful for storing very large or very small numbers, including those with fractional components. Floating point numbers often have small rounding errors, even when the number has fewer significant digits than the precision. Many times these go unnoticed because they are so small, and because the numbers are truncated for output. However, comparisons of floating point numbers may not give the expected results. Performing mathematical operations on these values will cause the rounding errors to grow larger. So imagine that this is going to be a very big problem if I want to do calculations about physics, especially on quantum mechanics and special relativity because of these rounding errors, which are not significant in very practical day-to-day uses, but in those situations, I think, yeah, it's probably going to make a very big difference. And so far, I think this was the most interesting part for me of this book. Yeah, I think I'm done for today. I have a bunch of stuff to do off stream. But I'll probably come back, I think, 2 days from now. Yeah, probably 2 days from now, I'm gonna keep reading this. And hopefully, in the future, I'll have more time so I can finish this faster. So, see you.